All right, let's get started with today's material. Pretty easy section today, and then you'll have the rest of the class for the test. So today we're starting chapter 2. Chapter 2 is on collections, different types of collections. The first type of collection that we're going to be talking about is called a list. You already have great intuition for what a list is, but what is a list? It is an ordered sequence of objects. We often call the elements in the list elements, or we call them members. Example, here's how you write out a list. You do a beginning parenthesis that says I'm starting the list. You write some object, like the number 1, followed by a comma. Then some other objects. So you have a bunch of objects in between two parentheses, comma separated. How many objects are in this list? 3. Nice. You can have whatever you want in a list. You're not limited to numbers. I can make a list composed of SpongeBob, the set containing 1, 2, 3, 2, and 3. How many objects are in this list? 4. SpongeBob, the set containing 1, 2, 3, 2, and 3. There's 4 objects in the list. Furthermore, I can have lists that have lists in them. There's nothing wrong with that. Here's a list containing the list 1, 2, and 3. How many objects are in this list? 2. All right, wonderful. Now, when are two lists equal to each other? So the list ABC is equal to the list XYZ if and only if A is equal to X, B is equal to Y, and C is equal to Z. Yes. All the elements have to be identical, and they have to be in the same order. For example, the set 1, 2, 3 is not the same thing, or sorry, the list. Those of you who know the difference, don't let me accidentally say that. The list. The list 1, 2, 3 is not the same thing as the list 3, 2, 1. They have the same objects, but in a different order. Those lists are not equal. Furthermore, the list 1, 2, 3 is not the same thing as the list 1, 1, 2, 3. If I add another 1 at the beginning of the list, that's a different list altogether. Make sense? Yeah. All right. We have a special name for a list that only has 2 elements in it. We call such lists ordered pairs. Ordered pair, a list with 2 elements in. Good? Okay. Example of list of ordered pairs. The XY plane. Talk about points on the XY plane. Anytime you talk about a point on the XY plane, you always use a list to represent a point. You would talk about the point 2, 5. 2, 5 is not a point. That's a list of 2 numbers. You're using that to represent the point 2, 5 at that location. Obviously, a point we represent that way. Right? Right. So you're used to using numbers, or you're used to using lists to represent points, and the point 2, 5 is very different from the point 5, 2. Those are talking about very different points. Okay. So that's lists, nothing to do with lists. Lists are going to be the first thing that we use to introduce us to the concept of counting. Now, you did learn how to count as a little kid, 1, 2, 3, 4, 5, and that's the most naive way to go about counting objects. You're going to learn how to count in this class, and you're going to learn how to count. Now, there's nothing wrong about counting that way, but we'll come up with more clever ways and more efficient ways to count things. So you're going to learn how to be able to answer problems with ease, like how many ways can I sit 9 people around a circular table? That'll become a question that's really easy for you to answer. Right now, you have no clue how to count that. Believe it or not, right? So we're going to teach you how to count. Again, imagine a first grader and you learn this. You ready to learn how to count? First thing we're going to count is 2-element lists. Start out nice and simple. So how many, often counting problems that we're going to see for the list section will be something of the form, how many lists can we make with such and such a requirement? So that's often what your counting problem is going to be like. So here's an example. How many 2-element lists, or how many ordered pairs, can I make from the numbers 1, 2, 3, and 4? So if 1, 2, 3, and 4 are the only objects I can put in the list, how many possible lists can I make? 16, right? Okay. And here they all are. There's all the possible 4-element lists I can make, or all the possible 2-element lists I can make with the numbers 1, 2, 3, and 4. Right? Okay. And you'll notice some nice patterns. Here's all the lists that start with the number 1. Here's all the lists that start with the number 2. Here's all the lists that start with the number 3. Here's all the lists that start with the number 4. So each row is keeping track of the first number, and each column is keeping track of the second number. Notice in this column, we're all 1s. In this column, the second number is all 2s, all 3s, all 4s. So 4 times 4 gives you 16. All right. So 4 squared, which is equal to 16. Let's do a more abstract problem, and then we'll go on with some more examples. So now, imagine I ask you, how many two-element lists can we make with n options per element? So if we're choosing from n objects, how many two-element lists can I make? So I'm not limiting you to just 4 options here. Now I tell you there's n options for each element. How many lists can we make? N squared. You see how he's getting that?
Yes.
How many elements are in this row?
Infinity.
Not infinity. N. Right?
Right, okay.
N could be any number. It could be 10, it could be 5, it could be 100. So this row has n elements. How many rows are there?
N.
There's n rows. So you have n rows of n elements. So there's n squared total. So now, this is your formula. This is how you count these things. So now I could ask you, how many two-element lists could I make if there's 200 objects to choose from?
200 squared.
200 squared. And that's the way I would prefer you write the answer. And notice that if you'll write it that way, you already save yourself some headache. Because Debbie tried to do the math real quick in her head, and she said 400, when the answer is in fact 40,000. Little bit different. Okay. Now, that was with all these lists. Now, what if I were to say, how many lists can we make with n options, but no repeating elements? So in other words, you can't have 1, 1, you can't have 2, 2, you can't have 3, 3, you can't have 4, 4, etc. So I say you can't have this one, you can't have this one, you can't have 3, 3, and you can't have this one.
And it's n squared minus n.
But how is he coming up with that? So now imagine, in this row, if we got rid of the 1, 1, how many elements would be on this row? How many lists would be on this row?
N minus 1.
N minus 1. There's n if we count all of them. If I get rid of 1, 1, how many are left? N minus 1. So there's n minus 1 on this row.
So it's n minus 1 squared.
Is that what it is? How many are on this row? N minus 1, so there's still n minus 1. All the way down, how many are on this row? N minus 1. Now how many rows are there? There's still n rows. So what's the math? What's the answer? N times n minus 1 is our answer. We have n rows of n minus 1. If you have 5 groups of 4 objects, how many objects do you have? 20. If you have 5 groups of 4 objects, you have 20 objects. If you have n rows of n minus 1 objects, you have n times n minus 1 objects. Right?
Right.
You following the algebra there?
Yes.
All right. Let's apply that really quick. Over here, if I got rid of the 1, 1, 2, 2, we said no repeating elements. How many are there here?
3.
How many are left?
Oh.
Sorry. I see what you were doing. You were telling me how many were in just one row.
There's
12.
3 times.
You know 4 squared was with repeats. Now it's going to be 3 times 4 without repeats. Right? This now has 3, this now has 3, this now has 3, this now has 3. We have 3 4 times. We have 4 times 3. Or 12. Right? Nice and simple. Now, maybe it's easier for you to remember it the way Jeremy said. Jeremy just distributed it here. He said, rather than n minus 1 times n, he said n squared minus n. Which still works. How do we think about it this way? N squared is counting all of them with repeats, right? Now how many are repeating elements? How many lists do we have with repeating elements? We have n of those. So he says, take all the ones you have in the beginning, now get rid of all your repeating elements. Same thing. You could have done that math the same way here. You could have started out with 4 squared, then minus 4. Same thing. Say 4 squared is total, and we're going to get rid of 4 elements. That leaves us with 12. Different ways of counting getting you the same answer. Good? Okay. Let's switch this up a little bit then. Now let's say that we have n options for the first element and m options for the second element.
M times N.
So how many lists do I have in this row? We have one for each of the numbers all the way up to m. We have one for the number 1. We have one for the number 2, one for the number 3, one for the number 4, all the way up to m. So there's m lists in this row. And in this row there's also m, and dot, dot, dot. And in this row there's also m. And how many rows do we have? N of them. So you have m, n times, or n times m. That's how you count it. Wonderful. Now, we're going to do a quick proof of that. Hopefully, now that I've written out the table here, following the proof will be pretty easy for you. Ideally, you'll be able to follow a proof like this without me first writing a chart like this down the road. So now we'll give you a proof. So there are n times m ordered pairs with n options for the first element and m for the second.
Okay.
How many possible ordered pairs can you make where you have n options for the first element and m options for the second? N times m. That's what we're proving. Now, we're basically going to be using the same thing we used in this chart, so hopefully you can follow the thinking here. First, we're going to construct a chart of all ordered pairs such that each row in your chart contains all the pairs that begin with a particular element. So this row is going to contain all the pairs that begin with the number 1. This row is going to contain all the pairs that begin with the number 2. All the way down to, this row is going to contain all the pairs that begin with the number n. You with me so far? What the order of these in a row are doesn't matter. We're just building our chart so that each row has all the elements that begin with a particular number. You follow me so far?
Yes.
With step 1? Step 2. Since there are n options for the first element, there are n rows. We made one row for all the lists containing a particular first element. Since there are n options for the first element, we're going to have n rows in our chart. Good. Okay. Since for each choice of the first element, there are m choices for the second, then each row contains m pairs. Each row has contained, this row has contained all the things I can pair 1 with. I can pair 1 with 1. I can compare 1 with 2. I can pair. I can pair 1 with 1. I can pair 1 with 2. I can pair 1 with 3. I can pair 1 with 4, etc. Each row has contained m elements. It has to contain all the pairings of the m objects with a particular first object. So I'll read that one more time and hopefully you understand it. Since for each choice of the first element, there are m choices for the second, then each row contains m pairs. Follow that? All right. Therefore, there are n rows of n pairs, or n times m pairs. Good? Follow the proof? Hopefully the chart makes it clear what I was saying there. All right, cool. Now, let's do a lot more examples, and then we'll get started. So our next example. View people's initials as 2-element lists. So we're going to ignore middle names. My initials would be the list D, T. Right? Yeah. So view people's initials as 2-element lists. How many are there? How many possible lists of initials are there?
4. Wait, just in our class?
No, total.
Oh.
For all the possible names of human beings on Earth,
Oh.
how many possible initials are there? Count them.
So
No,
many.
thank you.
You can have AA, you can have AB, you can have AC.
Oh, hey, that's not that hard.
How many are there?
26 squared.
26.
26 squared. When we're talking about a set of initials, how many options are there for the first initial?
26.
6.
I was thinking something else.
It must have been. There's, how many letters are in the alphabet?
26.
26. So that's how many options we have here. And for each of those 26 options, how many options do we have for how we can finish it?
26.
26. So there's 26 squared possible sets of initials. Make sense?
Yeah.
All right. What about without repeats?
26 squared minus 27.
Yeah, we can think about it the way Jeremy thinks about it. He says 26 squared is how many sets of possible initials there are. Now, how many are repeating initials? How many are AA or BB or CC? 26. So he says 26 minus 26. Perfectly valid answer.
Or you could say
You can write down your paper. Great. Another way you can think about it.
26 subtract 1 times 26.
Yeah. We have 26 options for the first initial, right? Now, how many options do we have for the second initial if it can't be the same as the first? 25. So you can think about it as 26 times 25. Also perfectly valid way to think about it. Or you can do brute force memorizing the formula. Know that you're getting rid of repeats and say, well, it's supposed to be n times n minus 1, so that's what I'll use. But it's good if you can think about how you're counting these things. So both of those perfectly valid answers, both of those are great answers. Don't simplify past that. Leave it like that. That shows me exactly what you were thinking. I know where it's coming from. If you just write some big number on, and the big number happens to be wrong, there's nothing I can do for you. You got it wrong. That's 0 credit. Right?
Yeah.
Right.
Okay. Let's do the next one. All right, we have a club that has 10 members in it.
Are you missing anybody?
Nope. We have a club that has 10 members in it. How many ways are there to elect a president and a vice president? You got 10 members of a club.
8.
How many ways? Where does this magic 8 keep coming from? How many ways can you elect a president and a vice president from the club?
And there's 10?
There's 10 members in the club.
Then 8's. Wait.
10 squared, 8 squared.
100.
Can the president and the vice president be the same person?
Yeah.
No.
Right, so that's why it's 8. That's where I got that magic 8 from, because you have to subtract 2 people because they had to.
All right. Overthinking it. How many options do we have for the president? 10. Right?
Yeah.
Now, once we have a president selected, how many options are there for the vice president?
10 times
9. So what's the answer?
9. 90.
90. That one's small enough numbers that if you just wrote 90, I'd figure out where you're coming from. You can also write as 10 times 9 if you want. Okay. Let's try another one. How many 3-element lists can we make using the numbers 1, 2, 3, 4, and 5?
5 cubed.
5 cubed. How are they coming up with that? Let's write out 1.
Because there's 5 numbers and then there's 3 spots.
Perfect. So for this spot, how many options do I have? 5. At least it's not 8. Okay. We have 5 options for what number goes there.
Right.
Right?
Right.
And for each of those 5 options, we have how many options for what goes here? 5. And for each of the 25 options we have for these two, how many options do we have for what goes here? 5. And so the answer is
125.
5 cubed, or 125. That's still a small enough number that if you want to write it out, that's fine. I'll know where it came from.
But without repeats, would it be 5 times 4?
Perfect. Yeah, well, if we did it without repeats, then now we have 5 options for the first element,
Then 4.
and then we only have 4 options for the second, and now we only have 3 options for the third. And now it's 5 times 4 times 3. And we have a notation for that. We call that 5 sub 3, like that. That means start at 5 and keep multiplying down for the first 3 elements.
Wait, wouldn't it just be 2?
For that,
Yeah. Because you start at 5 and then you go down 3 elements, but you really need to go down 2.
Including
you're noticing a nice pattern. You're noticing that when it's sub 3, the final element we multiplied by only was minus 2. But this is saying how many numbers we're multiplying together, starting at 5, counting down.
Okay.
So multiplying 3 numbers together, you'll notice that the last number you multiply has a 2 there. So just to make sure everyone's on the same page, let's say that I wrote 10 sub 4. What's that going to be equal to?
10 times 9 times 8 times 7.
Perfect. And so what he was noticing is it's kind of weird because we didn't end with times 6. He thought since 10 minus 4 is a 6, we should end with 6. But you end with 7. Good to note that. All right. We have that one next. Our club has 10 members. How many ways to elect a president, a vice president, a secretary, and a treasurer?
And 4.
What he just said worked. Did we really know? 10 4, yes. There's 10 options for your president, then 9 options for your vice president, and then 8 options for your secretary, and then 7 options for your treasurer. Right?
Right.
And so now notice that that's an easy thing for you to count now. You have 10 people in a room and someone asks a question. How many ways are there to do this? How many people could answer that question? Well, you could now. And it's actually a really simple question. It'll make you seem really smart. Especially if you first multiply it in your head and then say the answer. Because then you'll just say some big number and everyone will be impressed. When really all you have to be able to do in your head was multiply 4 numbers together.
That's it.
That's all it is.
That's all it is. Real simple. Counting is not hard. Right? You'll tell your younger siblings that. Counting is not hard. All right. So in general now, hopefully you're noticing a little bit of a pattern. Imagine that for some reason we did allow people to hold multiple positions. So someone could be the president and the vice president and the treasurer and the secretary.
It'd be 10.
Then what would the answer be?
10 to the power of 4.
10 to the power of 4. 10 times 10 times 10 times 10. So now, hopefully you've noticed a pattern. This is when you allow repeats, this is when you don't allow repeats. And now you can see why they chose this notation for this, to go along with this. Make sense?
Yeah.
So here's your general formulas. When we allow repeats, if there's n objects that we're talking about, if you have n objects and you're making k choices with those n objects, it's going to be n k times or n to the k. With no repeats, it's going to be n times n minus 1 times n minus 2 all the way down to n minus k plus 1, which is the same thing as n sub k.
Okay.
To n minus k plus 1. Hopefully we didn't get confused there. Let's just brute force use these formulas to answer these questions again. So we said if k is 4 and we have 10 objects, then the answer is n to the 4. Right? Looking at this formula, we're going to get the exact same thing that we had there. This formula says we do n times n minus 1 times n minus 2 all the way down to n minus k plus 1. So what is our n minus k plus 1? What's our n for the problem that we were doing, for this problem?
10.
10. What's our k?
4.
And so what's n minus k
6.
plus 1?
7.
So we keep multiplying until we get to 7.
Oh.
Which, so we said it's going to be,
Which is what we had there.
yeah, 10 sub 4 is going to be 10 times 9 times 8, and we keep going until we get to 7, and then we stop. That can be useful if you're doing a mass multiplication. Well, never mind. I won't say that. But so don't get confused by why there's a plus 1 there. It's the same thing that Phoenix brought up earlier. That's why there's a plus 1 there. Because in order to count 4 numbers, you need the plus 1 there. If we did all the way to n minus k, we would have actually counted k plus 1 numbers. Make sense?
Yep.
Cool. Because that formula is probably the hardest thing that we're covering today for students to grasp. And so you already got it. All right. So a couple more examples and we're done. So how many ways can we select 5 objects from a bag containing 3 items with repeats? So we got a bag that has 5 objects in there. I select an item, Phoenix selects an item, I select an item, then put it back, Phoenix selects an item, then puts it back, Debbie selects an item, then puts it back.
5 cubed.
How many possible selections could we have made? And he says 5 cubed. There were 5 options for, just to draw it out, there were 5 options for the item that I could have picked, then I put it back. There were 5 options for Hayden's choice, and he puts back. There were 5 options for Phoenix's choice, and he puts back. Right?
Right.
Okay. Let's try this one. Now we're going to select 3 objects from a bag containing 5 items without repeats. So the bag has 5 items in it. We're going to pull out 3 objects. How many possible ways can we do that?
5 times 4 times 3.
Perfect. There's 5 options for the first object.
Now there's
So we got a bag of 5 prizes in it. Each of you gets to grab 1 prize. So once he grabs a prize, it's no longer available, and there's only 4 prizes available to you. And then once you and him, then the last person, there's only 3 prizes available to them. 5 times 4 times 3.
Did we do the one above it, right?
This one?
Contains 3 items, not 5 items.
Select 5 objects. Oh, thank you. We did do this one wrong. Good eye. We're pulling 5 objects out of a bag containing 3 items. So we're pulling out 5 times. Sorry. My bad. Good catch.
So it's 3 to the power of 5.
3 to the power of 5. 3 options, 3 options, 3 options, 3 options, 3 options, 3 to the 5. Thank you.
What if you did it 5,000?
On this one? Alright, let's read it.
Because there's
Now we're going to select 5 objects from a bag with 3 items without repeats. How many options do we have for, so we got 5 objects.
Did you even do that? Yeah, there's so 5.
How many options do we have for the first object?
3.
3.
Then 2.
How many for a second? 2.
Then 1.
Then 1.
0.
Then 0. Then
Negative 1.
negative 1. Multiply them all together, you get negative 6. No, that's nonsense.
You got 0.
Yeah, you can't.
There is no way to do that.
So
So be careful just brute force following your formulas. Make sure your answers actually make sense. Alright. Yes, do not tell me negative 6. Or don't write nonsense. Here's an example of me writing nonsense. How could we have written this? We could have written this as 3 sub 5. 3 times 2 times 1 times 0 times negative 1 is negative 6, right?
no, 0.
So you can actually still follow the formula, and it works. The formula happens to still work. You're right. I may go back and forth. You better be thinking. The formula still works. Because it's going to give you 0, which is the right answer.
So back there when you were saying it's nonsense and it equals negative 6, you were wrong.
Negative 6 was a nonsense answer. But negative 6 is not the product of these numbers.
Okay.
All right. We're back to making sense. I want you to follow your own thinking rather than some formula. Yes, the formulas will happen to work. I prefer you to just be able to think about it.
Okay.
Because sometimes you make mistakes using the formula. Because if you try to use this formula and you evaluate this, I would bet that 1 in 50 times a student accidentally puts negative 6. Which makes 0 sense. When their gut was already screaming, it's 0, obviously you can't do this. So there's a danger in just blindly using a formula, because there's a small chance that you accidentally misuse the formula. But yes, the formulas will always still work if you perfectly use them. But I'd rather you be able to think about it. Because even I make mistakes using formulas all the time. And I often have to fall back to, does that answer even make sense?
So,
Comma phenomenon.
so
Huh?
did you on purposely say that it was negative 6?
Yeah, that was on purpose to throw you off. Because it's one of the ways I've seen that formula misused. Is they go to do something like this, and they spit out some negative number. Which is bad. Right, makes no sense. Okay, so that's it for new material today. Not bad, right? Nice, easy.
Yeah.
That will be on the test we're taking 2 weeks from now. These tests come quick.
Easy.
Okay, so I had a question. So, you know that symbol that's like 2 divides 8?
Yes.
Can you write that out?
2 divides 8.
So that is how you say it, right?
Yes. 2 divides 8. You can also read that as 2 is a factor of 8.
Right.
Yes.
Okay. Sweet.
And this is equal to 4, right?
No.
No, what's it equal to?
True.
It's equal to true. This is a proposition. This is something that's true or false.
Yeah.
It's not an operation. We're not dividing anything.
I know that's.
Apparently Debbie was wrong.
No, I was right.
Oh, Debbie was right. Okay.
No, she was wrong.
Alright. You
No,
guys can
I
arm wrestle
didn't.
for it later. Any other questions that you want on lecture?
Will you go over
think
this proofs with us?
Will I go over what?
Disproofs?
Prove something false, proof by counterexample. Sure. Prove the statement, all prime numbers are odd, false. Observe that 2 is prime and is not odd. Square box.
Okay.
So when you prove a statement false, you find a counterexample. So the one that you did was to prove the statement false that A divides B and B divides A implies A is equal to B. This is not true. And the counterexample is observe that negative 8 divides 8 and 8 divides negative 8, but 8 is not equal to negative 8. So this being true did not imply that was true. Any other questions we want to lecture?
Question. So,
Go ahead.
with the prime thing, when I wrote it out, I says,
That's what I
I pretty much proved that 2 and 3 are prime. And then I said that 3 plus 2 is 5, and then proved that 5 is prime, not composite. Because it was saying like I think it was the sum of 2 prime numbers is composite or something like that. Yeah,
Oh,
disprove it.
and you're supposed to disprove it.
Did I
That
have
works.
to like prove that they were prime? Or could I just have said 2 and 3 is prime?
It's enough to just state it. You don't need to prove that that number's prime. Because the only way to prove that a number's prime is to say, observe that 2 doesn't divide it, 3 doesn't divide it, 4 doesn't divide it, therefore the only common divisors are 5 or 1 and 5.
Well, I just said.
You can use the fact that it's well known that the prime numbers we know are prime. Yeah.
Okay.
No one will follow you for that.
think you're right.
Okay, cool.
Debbie would have been able to follow that, right? And if Debbie can follow it, you're good. All right. Any other questions you want to lecture? Okay, cool. Stop that.